Hi Chem 151 students, and welcome back to our continued discussion of acid-base titrations. So last week I showed you about an hour-long work through of a strong base, weak acid titration. But now we're going to do a weak base, strong acid titration. The strategy that you're going to use to do these will be the same as we had before. But sometimes, it's good to see an example, the weak base, strong acid. They are a little different. For example, we're dealing with a base here, so we're going to have a Kb for our base, not a Ka, because it's not an acid. But the general feel for the steps will be the same. We need to evaluate whether we are before the titration has started. For example, with 0 milliliter of our titrant added, whether we're before the equivalence point, at the equivalence point, or after the equivalence point, because the way we approach the second step, the equilibrium step, will depend on where we're at in the titration. So here's the problem that I'm going to do, and it's the same problem as you're going to have in the homework. I do have a few other volumes that you'll calculate, and I also have you graph the results so you can see how it results in a titration curve. So the problem reads, find the pH during a titration of 20 milliliters of 0.1 molar triethylamine, which has the formula right here. It has a Kb of 5.2 times 10 to the minus 4, and it's being titrated with 0.1 molar HCl, and we have the following amounts of titrant that have been added. So let's start with 0 milliliters of titrant here. So we're starting with just the weak base. This is a weak base equilibrium. No HCl has been added yet, so we don't have to worry about any stoichiometry or neutralization step here. We just have the weak base. So this is basically like a chapter 18 problem we're doing. Now this is a big long name for this weak base, so I'm just going to call the weak base B. Just like we did for the acid, we called the acid HA. For the base, we're just going to call it B base, and that will make writing things down easier. So what we have right now is we have no HCl. All we have is the weak base B in water. So that's what we write as our reactants. The weak base is going to be accepting a proton from water, and so it will get the H+, and so it will be in equilibrium with BH+. And when the water loses the H+, it makes its conjugate base, which is the hydroxide ion. So now we are ready to make an ice table. We'll go straight to equilibrium. Again, we haven't added any strong acid, so we don't have the first step where we do a stoichiometry of the neutralization, because no neutralization has happened. All we've got is the weak base in water. And so we're going to set up an ice table now to evaluate this equilibrium. We're given an initial concentration of the base. It is 0.100 molar, so we're going to put that in right here for the initial concentration of the base. We'll say the initial concentration of hydroxide is about 0. Of course, we know in pure water it's 1 times 10 to the minus 7 molar. We're going to assume that's very small compared to what we're going to get, and so we'll call it about 0. And then we have no BH+ at all, not yet, not before the equilibrium has happened. And then our change here for the base, of course this reaction has to go forward because there are no products. So the change here will be minus X for the base, and plus X for hydroxide, and plus X for the BH+. So our equilibrium concentration for the base will be 0.1 minus X, and for hydroxide and BH+, it will be X. Okay, so Kb, the expression is going to involve hydroxide on the top and BH+, since those are our products, and our reactant here on the bottom will be concentration of B. Water, of course, is not included because it's a pure liquid. And so if we plug in the values now, it's going to be X for hydroxide, X for BH+, and it's going to be 0.1 minus X for B. And it has 4 sig figs here. I didn't write it there. I should have, but it's 0.1000 minus X. And so we get, and that is equal to the Kb, 5.2 times 10 to the minus 4. Now we do have something to be careful of here. And this is because I wanted to give you at least one problem where the simplifying assumption is not going to work. So you can see that our KB is kind of high here. And so we're going to have to do our pre-check and compare our initial concentrations to our KB here and see how much bigger than KB it is. So we're going to copy this over to the next slide. So 5.2 times 10 to the minus 4 equals x times x over 0.1 minus x. Okay. And at this point, before we do our simplifying assumption, we should do a pre-check. So in the pre-check, we take the initial concentration and we divide it by the KB to see, is this greater than 400? And so we would plug this into our calculator here, and we've got 0.1 divided by 5.2 times 10 to the minus 4, and we get about 192. And that is not greater than 400. That is less than 400. So our pre-check fails here, which tells us that we're going to have to solve the quadratic equation to determine x. This does happen sometimes. So let's start to apply the quadratic equation now. The first thing we're going to have to do is multiply both sides by 0.1 minus x. And I've cut off a couple of sig figs here just so that it fits a little better because I do have limited space. But remember, we've got 0.1 with 4 sig figs here, even though they're not written. Just keep that in mind. So I'm going to multiply both sides times 0.1 minus x. And so that's going to cancel 0.1 minus x on this side, and then we'll have 5.2 times 10 to the minus 4 times 0.1 minus x. And that will equal to x times x, which is x squared. Now we need to get this equation into the quadratic form. And so we're going to have to multiply this 5.2 times 10 to the minus 4 times each of these. So for times 0.1, that gives us 5.2 times 10 to the minus 5. And then we have minus 5.2 times 10 to the minus 4x. And so now what we're going to do here is we're going to add here. We're going to add 5.2 times 10 to the minus 4x to both sides, so that will cancel it there. And we're going to do that over here too, plus 5.2 times 10 to the minus 4x. And then we're going to subtract 5.2 times 10 to the minus 5. And so that's going to cancel here. So we cancel both of these on this side so that we can get 0 on this side. And so we'll also then subtract here. So let me make sure I don't write over my next line here. And we're also going to subtract, and I'll put it right here, minus 5.2 times 10 to the minus 5. We're adding that there. So we're going to get x squared plus 5.2 times 10 to the minus 4x minus 5.2 times 10 to the minus 5. And so there is our equation now, and that all equals 0. So in our quadratic here, 1 is going to be equal to, A is going to be equal to 1. So this is our A, and 1 isn't written here, but it would be 1. So our A is 1. Our B is this guy right here. And our C is negative 5.2 times 10 to the minus 5x. So we're going to plug that now into our quadratic equation. And so the quadratic equation, so our quadratic equation, just as a reminder, I'll write it up here. It is minus b plus or minus the square root of b squared minus 4ac over 2a. Okay. And so we're going to plug these in now. So minus b, this is going to be minus 5.2 times 10 to the minus 4. That goes right there. Plus or minus, and this is what x equals, by the way. X equals this. Okay, and then we have plus or minus b squared, so 5.2 times 10 to the minus 4 squared goes right there. Minus 4 times a is 1, times c, which is negative 5.2 times 10 to the minus 5. And that is divided by 2. Okay, And so let's do everything that's underneath the square root first here. So let's calculate that. So we're going to have 5.2 times 10 to the minus 4 squared minus 4 times 1 times negative 5.2 times 10 to the minus 5 equals. And we get about the 2 sig figs 2.1 times 10 to the minus 4. So we're going to keep everything else the same, but we're going to put under the square root 2.1 times 10 to the minus 4. Okay. And so now we can calculate both the positive form of x and the negative form. I'm just going to tell you right now. Let's take a look. We know that a negative concentration is not going to make any sense, because notice that the concentration of hydroxide is equal to x. A concentration can't be a negative number. So the number here that is negative, the minus, we can ignore the minus because that's going to produce for us a negative number. So we can ignore the minus and we can just go with the plus here. And that's going to give us our value of x. So let's go back to the calculator now and calculate our value of x. It's going to be negative 5.2 times 10 to the minus 4 plus the square root of 2.1 times 10 to the minus 4. Okay, that equals, then we're going to divide that by 2. And so we get x is about 7.0 times 10 to the minus 3. That is x. Or to here, I got a little bit off, a little bit different here, I think, because I didn't round in between. I had 6.96. Here I have 6.99. But it's only good to the 9 anyway. I just kept an extra digit. And so I'll always underline if I keep an extra digit there. But now we have x, that's the concentration of hydroxide. So we can't get pH directly, but we can get POH. So POH is going to be the negative log of the hydroxide concentration. So POH is going to be the negative log of this number, 6.96 times 10 to the minus 3. So I'm going to do negative log, and let's just do 6.9. It's really good to 2 sig figs anyway. It's 10 to the minus 3. That would be 7.0, I guess, really. I'll just go with the, either way, it's gonna, seems I rounded in intermediate steps, so I'll just put the 6.96, but it's gonna come out the same either way, because we're gonna do the 2 after the decimal. So for the result, and so we're gonna say 2.16 for the POH. 2.16. Okay, and then we know pH and POH add up to 14, and so pH is 14 minus the POH. pH is 14 minus 2.16. 14 minus 2.16, and that equals 11.84. 11.84 is the pH. Okay, so this was just a standard chapter 18 weak base equilibrium problem. There was no titration going on here because 0 milliliters of titrant have been added. What made this problem a little bit tougher than some of the ones we've done before was that KB was not so small. And so the result was that our pre-check failed. The KB was not small enough for the initial concentration divided by the KB to be less than 400. And so we had to solve the quadratic equation to avoid too much error in our calculation. So it's been a while since we did one with the solving the quadratic equation. So I wanted to make sure to remind you that that will happen sometimes. It tends to not happen so much with buffer problems for a reason you might expect. It's because, remember, buffers don't result in a significant change of pH when you add acid or base, and so X is usually quite small for those ones. And so that's why the Henderson-Hasselbalch equation works so well for buffers, because X is usually negligible. but it's important to keep watching out and to keep up your pre-check to make sure that you can, in fact, use the simplifying assumption. A post-check is generally good too. A post-check, you can usually eyeball it a lot of times. X is often much, much smaller than your initial concentration when the pre-check is good. So, but a pre-check is always in order, especially in situations like this where K is quite big. Okay, and so that was before any titrant has been added. Now let's go start the titration. So now at this point we will have the same base, but now we've added 10 milliliters of the titrant HCl. So now we're doing a titration. We need to do the 2 steps of a titration problem, the stoichiometry step and then the equilibrium step. Before we can do the stoichiometry step, like I said, I do things a little bit differently than your book. I like to do a dilution to calculate the initial molarities of everything and then work in molarities all the way through the problem. And so that's what I'm going to continue to do here. You'll notice again that your book likes to turn the volume and the molarities into moles, do the stoichiometry in moles, and then calculate new concentrations with the new volumes. That is the same thing essentially, but I find my way a little bit easier to follow. I don't care which way you show me on your exams when you write the problems out. Either way is fine. Okay, so we should, though, now that we have a new volume, we should calculate new concentrations for everything. So the solutions have been mixed, so the volume is changed. We're going to calculate the new concentration using M1V1 equals M2V2, solved for M2. So it's M1 times V1 divided by V2. And our V2, or our V total, is the 20 milliliters of the weak base solution that we started with, plus the 10 milliliters of the HCl solution that we added, for a total of 30.0 milliliters. Now, again, we're going to call the weak base B. We're just going to keep calling it B. So the initial concentration of our HCl here is going to be its initial volume, 10 milliliters, that's V1, okay, times the concentration, M1, that's 0.1 molar, divided by the V2, the total volume at the end, which is 30 milliliters, okay? And so then our concentration here is this 10 times 0.1 divided by 30. We can put that in our calculator if we want to. 10 times 0.1 divided by 30. And to 4 sig figs, we get 0.03333. Okay, and then for the weak base, its initial molarity is 0.1 molar, but its initial volume is 20 milliliters. So on top, we have 20 milliliters for volume 1. We have 0.1 molar for molarity 1 for the base. And its final volume is the total volume, 30 milliliters. So here we have 20 times 0.1 divided by 30. And we get 0.66666, and to 4 sig figs, I've rounded the last one to 7 here. Okay. And so now we've got our initial concentrations for the HCl, the strong acid, and the weak base. So now we're ready to do step 1 in our titration, where we have a complete reaction of the strong acid until it is all gone or until the weak base is all gone. So we assume 100% reaction for our stoichiometry step here. All right, so we're continuing, same problem, but the equation that we write here is the neutralization of our weak base, which again we're going to call B, and our strong acid HCl. So our reactants in the equation are our base B and our strong acid HCl. And our concentration of HCl from the previous slide was 0.3333 molar, and for the weak base it was 0.0667 molar. And we're going to react these two together. So these are the reactants, weak base plus HCl. We have a one-way arrow here because we assume 100% reaction of the strong acid in our stoichiometry neutralization step. And this is going to produce for us it's going to give the H plus to the base, so we'll have BH plus, and we'll have chloride ion remaining. Now, HCl is a strong acid, so in solution, HCl breaks up into H plus and Cl minus aqueous. So we can see that chloride here is a spectator ion. If we remove it, removing the chloride spectator, we have B and H plus make BH plus. Again, you don't have to remove the spectator, but I do find it makes things a little cleaner. And since HCl is a monoprotic acid, if we have 1 mole of HCl, that makes 1 mole of H plus. So our concentration of HCl is the same as the concentration of H plus, 0.03333 molar. Now we can do our stoichiometry in a chart, but we shouldn't call it an ice table. We should call it a start, change, end of stoichiometry table. And our initial concentration of our base is 0.06667 molar. Our initial concentration of our H plus or HCl is 0.03333 molar. And for our BH plus, its initial concentration is 0. So we have this reaction is going to go forward 100%. So this is going to be until all of the H plus reacts. So we know that our change here is going to be all of the H plus. So it will be minus this amount, minus 0.03333, because we're assuming in the stoichiometry step, the strong acid reacts until it's all gone, or if the base runs out, until it's all gone. So we're going to have none of the strong acid left, because again, we assume 100% reaction. So these are 1-to-1, so if this much of the acid reacts, that same amount of the base has also reacted. So our remaining amount of base is 0.06667 minus 0.03333. That is 0.03334. And our BH plus here, this is going to be plus 0.03333. And so the result is 0.3333 for BH plus. So now we are done with our stoichiometry step. We can move on to our step 2 equilibrium. Notice that we have significant concentrations of our weak base and its conjugate acid. This is going to be a buffer. And so we will be able to use the Henderson-Hasselbalch equation for this to solve for the pH in this case. Okay, and so now we're going to go to step 2, equilibrium. Again, we're calling the weak base B. And so at this point, the equilibrium involves the weak base behaving like a base, or equivalently, and just copying from the last slide here, we have weak base 0.03334 molar, and the conjugate acid 0.03333. Now the thing about the Henderson-Hasselbalch equation is it's stated in terms of acids, pKa. There is an alternate version that involves pKb. It works very similarly, but instead of teaching you 2 equations, I just have you adapt yourself to the one equation. I don't mind if you end up discovering that base form of the Henderson-Hasselbalch equation and using it. That's fine. I don't mind that. I just don't want to overwhelm you with too many different equations. So anyway, our equilibrium here is the weak base and water, and that's in equilibrium with hydroxide. Okay, that's again the weak base behaving like a base, and grabbing a proton makes hydroxide, and then we get the conjugate acid BH plus. This is a buffer though, so since it's a buffer, we can use the Henderson-Hasselbalch equation, but again, the Henderson-Hasselbalch equation has been stated for us in terms of Ka's. So what we can do instead is we can find the Ka for BH plus, and that will allow us to determine the pH using the Henderson-Hasselbalch equation. So remember that Kb for a weak base times Ka for its conjugate acid multiplied to Kw. And so if we want the Ka of BH plus, we take the Kw and divide by the Kb of the base. And so Kw is 1 times 10 to the minus 14. The Kb for the base is 5.2 times 10 to the minus 4. So we're going to divide those. 1 times 10 to the minus 14, divide by 5.2 times 10 to the minus 4, and we get a 1.92, where the 9 is the last sig fig, times 10 to the minus 11. So I've underlined the 9 here, that's the last sig fig. So now that we have a Ka, now we can use the Henderson-Hasselbalch equation like we're used to. The base is going to be the weak base here, B, and the acid is going to be the conjugate acid, BH+. So pH equals pKa plus base over acid, log base over acid. And so for the pKa, we're going to take the negative log of the Ka, 1.92 times 10 to the minus 11. 1.9 is the last sig fig there, plus the log of the base concentration, 0.033334, divided by the acid concentration, 0.03333. These are essentially the same, so we have the log of 1, and that, as you know, goes to 0. And so the pH here equals the pKa of the conjugate acid here. So let's calculate that. It's going to be the negative log of 1.92 times 10 to the minus 11. And so we get a pH of 10.72. 10.72 is our pH. Okay. And so, like I said, the strategies are the same, but here, because we're dealing with a base, we had the extra step of if we want to use the Henderson-Hasselbalch equation, which is written in terms of Kas, we need to get the Ka for the conjugate acid. So that was a little extra step compared to what we would do for a strong base, weak acid titration. But the strategy overall is the same. Because we have a buffer, we could use the Henderson-Hasselbalch equation. The big extra step was this one right here that we had to do. We had to find the Ka because we didn't have it. Okay, so that's dealing with a strong acid, weak base titration when we're before the equivalence point. In fact, at this point, we were at the half equivalence point. The halfway equivalence point, and so the pH equaled the pKa for the conjugate acid there. And of course, this is still a weak base equilibrium. We're still on the basic side of the pH here, which makes sense for us. Okay, so next we're going to look at the addition of 20 milliliter titrant. Before we do that, I do want to do a post check here, just to confirm for you that the Henderson-Hasselbalch equation did work even for this situation that we're in, where the Kb was large. So remember, when we just had the base equilibrium, we had to deal with using the quadratic equation because the Kb was too large. So what we'd like to do is check, based on the pH that we determined, would X have been too big and for us to use the Henderson-Hasselbalch equation? And so what we can do is we can kind of go backwards, and based on the pH we found, figure out what that means X would have been, and determine, was that X too big or not? Was it too big compared to the initial concentration? So again, we're calling the weak base B here, and the weak and we had these initial concentrations. The weak base, we determined that the pH was 10.72 at equilibrium. So we were dealing with our weak base equilibrium, the weak base with water, accepting a proton, making BH plus and hydroxide. And we had set up this ice table where we had the initial concentration of the base and the conjugate acid. And if we were to set up an ice table like this, it would have been minus X here for the base, plus X for hydroxide, and plus X for BH plus. This reaction has to go forward because there's no hydroxide here. It can't go backwards. And so our equilibrium concentrations would have been 0.03334 minus X for the base, and X for hydroxide, and 0.03333 plus X. So the question here is, if our pH was 10.72, how much was X? Well, what we can do is we can figure out if the pH is 10.72, what is the hydroxide concentration? That will be equal to X. Then we can compare X to our initial concentrations and make sure that X is not more than 5% of our initial concentration. So the POH is 14 minus the pH here. We got a pH, so we can get the POH. The POH will be 14 minus 10.72, 14 minus 10.72. So our POH is 3.28. Now what we can do is we can take the antilog of the negative POH to get the hydroxide concentration. So that's the antilog of the negative POH, and that will give us X, or the hydroxide concentration. So we're going to take the antilog of the negative POH, antilog of negative 3.82. So we hit shift and log, that gives us the antilog. Then we hit the negative key and 3.28. And we get 5.2, let's see, 5.2, yeah, with 2 sig figs, times 10 to the minus 4 for our X. And so the question here now is X greater than 5% of our initial concentrations here? So we're going to take X and put it over the initial concentration and turn it to, here we have X. We're going to divide it by our initial concentration, 0.03334, and see, is that greater than 5%? Is X greater than 5% of this? And so let's calculate it. 5.2 times 10 to the minus 4, divide by 0.03334, and then times 100 to make it a percentage. And we get about 1.6%. So 1.6% is less than 5%. So we were safe in using the Henderson-Hasselbalch equation. The X that we determined was less than 5% error from if we had done the ICE table and solved and then plugged this in and solved for the quadratic equation. We would have gotten a little less error, but this is totally acceptable. And generally that will be the case. So you can basically always feel safe using the Henderson-Hasselbalch equation as long as you actually have a buffer. Oh, by the way, yeah, my head's in the way a little bit, but yeah. So you can actually feel safe using the Henderson-Hasselbalch equation as long as you've got significant concentrations of both an acid and its conjugate base, or here the weak base and its conjugate acid. Same thing, said a different way. So our check here was okay, and generally you don't need to do a check as long as you're using the Henderson-Hasselbalch equation when you have significant concentrations of the acid and the conjugate base. I just wanted to do a post check and determine X and compare it to the initial concentrations to show you that the Henderson-Hasselbalch equation did work even when we had a relatively large KV here. It was because we have significant concentration of the conjugate base, so we don't have huge shifts in the pH because we have a buffer here. So the X is small due to that fact. Okay, now it's time to move on in the titration. Now we will have added 20 milliliters of our titrant. You probably can tell right away that since we have 20 milliliters of 0.1 molar base, 20 milliliters of 0.1 molar acid, we're going to be at the equivalence point here. But we can verify that as we move forward. The solutions are being mixed, so I'm going to do like I usually do and determine the concentrations of each after they have been mixed. So our new volume is 20 milliliters of our base solution plus 20 milliliters of our acid solution, for a total of 40 milliliters of solution. And so we're going to call the base B here. So our concentration of HCl will be its initial volume, which is 20 milliliters, times its initial concentration, 0.1 molar, divided by the final volume, 40 milliliters. And so we get 20 divided by 40 is 1/2. So 1/2 of 0.1 molar, it's 0.05 molars to 4 sig figs there. For the base, it's the same thing. We're starting with 20 milliliters, volume 1. Molarity 1 is 0.1 molar. Volume 2 is the total volume, 40 milliliters, so we get the same value here. So we are at the equivalence point. We have added the same amount of acid as we have a base. So now that we've dealt with the volume change, we're ready to start step 1, the stoichiometry step, where we assume 100% reaction of the strong acid. And so our stoichiometry step is going to be the reaction of the strong acid with the weak base, and assuming 100% reaction. So moving forward, step 1, stoichiometry. We'll call the base B as usual. And from the previous slide, we had 0.05 molar HCl and 0.05 molar of the weak base. And so now we're going to write down the reaction that's occurring, the neutralization. It's the weak base plus HCl neutralizing one another. The H plus is donated to the B, and so we get BH plus, and remaining is the chloride ion. Again, chloride ion is the spectator here, so if we remove it, we have the base, we have just H plus here, and again, one-way arrow, 100% reaction, and the product here is now just BH plus. And at this point, we can do our stoichiometry in the table. So we set up a start, change, end of stoichiometry table. Our initial concentration of the weak base is 0.05 molar. For the HCl, it's 0.05 molar. And for the BH plus, it's starting at 0. Again, we assume 100% reaction of the strong acid. So all of this is going to be gone. So we'll have minus 0.05 molar, leaving us with no strong acid left. And that same amount of the base is going to react. So we have none of the base remaining. We're going to have, since this is 1-to-1, we're going to have plus 0.05 molar of the conjugate acid here. So all we have left in solution is the water, of course, and the BH plus. So this is going to turn out to be a acid equilibrium here with the remaining BH plus. Our reactants will be BH plus and water for the equilibrium. Notice, we're not going to write for the equilibrium, the weak base, because we're assuming that none of it's left. At equilibrium, will there be some? Yes, but we're dealing with that in the next step, the equilibrium step. So for our equilibrium step, we're going to keep in mind here our concentrations. We're going to put these over to the next slide. So equilibrium, still calling the weak base B. From the previous slide, we had 0 molars remaining of our weak base and 0.05 molars of our BH plus. This is very important for deciding which equation you write. As I said before, the math is, you kind of started to do this again and again. The math should be starting to become more routine for you. What's hard is deciding what is it that you're dealing with in your flask. What is in your flask? What should you write for your reaction? What is in your flask right now is the conjugate acid and water. So that's what we're going to write here, the conjugate acid and water. And it's going to be behaving as a weak acid. It will give its H plus to water in this equilibrium. And so the water will pick up the H plus, going from H2O to H3O plus, and the BH plus will have lost its H plus, so now it's just the conjugate base. So we have a weak acid equilibrium with the BH plus here, but we need the Ka. We solved it previously, we can solve for it again. We need K for this equation, which is the Ka for BH plus. It's behaving like an acid. So we to find that, we take the Kw and divide it by the Kb. We did this on a previous slide. So it's going to be Kw, 1 times 10 to the minus 14, divided by 5.2 times 10 to the minus 4. And as we saw on the previous slide, the Ka was 1.92 times 10 to the minus 11. The 9 is the last sig fig here. Okay, so I'll move my head out of the way when we need that again. All right, and so now we're going to set up our ice table. We can't use the Henderson-Hasselbalch here. Very important. At the equivalence point, you cannot use the Henderson-Hasselbalch. You have to set up an ice table because, remember, the precondition to using the Henderson-Hasselbalch is you have to have significant concentrations of the acid and its conjugate base. You don't have any of the conjugate base. You only have the acid. That's why we're dealing with this weak acid equilibrium. And so our initial concentration of the BH plus will be 0.05 molar. For H3O plus, it's about 0. And for the base, we're assuming we have none left. We're just dealing with the equilibrium to find out how much of that we'll have. This reaction is going to go forward since we have no products. So minus X here, plus X for the H3O plus X for the base. For our BH plus is 0.05 minus X. For H3O plus, it's X. And for the base, it is X. So now let's write the expression for the Ka of BH plus. It's going to be on the top of the fraction hydronium and the weak base concentration, and on the bottom of the fraction BH plus concentration. Water we don't include because it's a liquid. So now we're going to plug these in. We're going to get X times X on the top, X here for hydronium, X here for the base, and for the conjugate acid, it's 0.05 minus X. And so now we're going to take all of this and we're going to bring it to the next slide along with our Ka for the BH plus. 1.92 times 10 minus 11, where 9 is the last sig fig. So let's take all of this and write it on the next slide. So Ka is hydronium times base over BH plus, so that was X times X over 0.05 minus X. We should do a pre-check, although you can probably see Ka is really small here. So our pre-check this time will pass. We take our initial concentration, 0.05, we divide it by the K. We get that this is far, far greater than 400. So we're totally safe here. X is going to be small. So on the top, we'll have X squared. On the bottom, we'll have 0.05 minus X, but the X is so small, we can just say this is about the same as 0.05. So now let's multiply both sides times 0.05. That will cancel here. Times 0.05 right here. Let's now calculate that. So X squared on this side, and on this side 0.05 times 1.92 times 10 minus 11. 0.05 times 1.92 is 10 to the minus 11. All right, and that gets us 9.6 times 10. Whoops, did I put that wrong? I have 9.8 for some reason. Oh, because I didn't. Okay, I have to square root 2. Okay, so now that gets X squared is equal to this. Now we take the square root of both sides, square root of that, and we get 9.8 times 10 to the minus 7. And X is the concentration of hydronium, as we see here. So to get the pH, we simply take the negative log of that concentration. A negative log of the hydronium concentration, that is negative log of 9.8 times 10 to the minus 7. Negative log 9.8 times 10 to the minus 7 equals, and we get 6.01 for our pH. All right, and so now we've determined the pH of this weak base strong acid titration at the equivalence point. Okay, and next, this is of course going to be after the equivalence point. We've added even more of the HCl solution. So again, first thing to do is to account for the new volume and determine what the concentrations of everything are. So the volume change, we calculate new concentrations here. For the total volume is going to be 20 milliliters of our base plus 25 milliliters of the acid for a total of 45 milliliters. And we're going to call the base B again. For the HCl, its concentration is its initial volume, 25 milliliters, times its molarity 1, its initial concentration 0.1 molar, divide by volume 2, which was the total volume here, 45 milliliters. So 25 times 0.1 divide by 45 equals 0.05556 to 466 right there, 5 repeating there. Okay. And for the base, its initial concentration is 20 milliliters, that's volume 1. Its molarity 1 is 0.1 molar. And its molarity 2, the final molarity is, volume 2, its final volume is 45 milliliters. So that will give us the final concentration, 20 times 0.1 divided by 45 equals, and we get 0.044444. Okay, so now we have our initial concentrations to go into our first step, the stoichiometry step, where we assume 100% reaction of the strong acid, or if it runs out first, the weak base. Okay, so our reaction here, well, let's get our concentrations from the previous slide. For HCl was 0.05556. For the weak base, triethylamine, it was 0.0444 molar. Our reaction is going to be the neutralization, weak base plus the strong acid for our stoichiometry. And we assume 100% reaction of the strong acid. Okay, and this is going to donate the proton. Again, we'll get BH plus and chloride ions. Again, it's kind of nice if we remove the spectator chloride ions. That will leave this as H plus, and this will go away. Chloride. So now we do our start, change, end of stoichiometry table. We put in our initial concentration of base, 0.0444 molar. For the HCl or the H plus, it's 0.05556. And for the BH plus, we're assuming 0 to start. After the equilibrium, of course, there's always some, but these assumptions help us to do the problem easier. Now, this time, the base is going to run out before the acid. And so our change is going to be 0.00444, because that's going to leave us with 0 of the base. So that same amount of H plus will react, 0.0444. So that's going to leave us with 0.1112 molars for the H plus. For the BH plus, it will be plus 0.0444. So our concentration of BH plus will be 0.0444. Now, what is remaining in our solution? We have the weak acid, BH plus, and we have directly H plus. Okay, so this BH plus will contribute a little bit to the acidity of the solution, but nothing compared to just dropping in straight H plus from the strong acid. So again, because we're after the equivalence point, we're going to have excess of, in this case, the strong acid, and that is going to dominate the pH. This contribution from this weak acid will be negligible compared to H plus directly. So at this point, from the previous slide, we have HCl 0.01112 or H plus 0.0112 and BH plus 0.0444 molar. Again, we have excess strong acid here, so there's no equilibrium really. I mean, this is going to contribute a little bit with its equilibrium, but it's going to be really stifled by the fact there's already tons of H plus in the solution. That's what's going to dominate the pH. So past the equivalence point in this case, the excess strong acid dominates. H plus is the strongest acid there is in water, much stronger than BH plus. So the contribution due to BH plus will be negligible. This happens when we pass the equivalence point. And so if we want the pH, we take the negative log of the H plus concentration. The contribution of BH plus to pH is negligible, so the pH will be the negative log of the H plus concentration of the hydronium. So that will be the negative log of 0.01112. And so we do that, negative log of 0.01112. And that gives us a pH of 1.95 is the pH. And of course, this makes sense. We dumped in a bunch of extra strong acid that was concentration 0.1 molar. So that pH is going to be steadily approaching pH 1, which is the pH of this HCl solution. So after the equivalence point, there's not really a equilibrium to speak of. It's the excess strong acid that dominates here. And so we use its concentration to determine the pH. And so that was a run through of a strong acid weak base titration. As you guys can see, going through a problem like this at every single step of the titration takes some time. Really, each of these problems I showed you was like, 3-4 separate problems. But I wanted to show you the progression of that. As you move through the homework, you'll do the same problem, but there's a few additional volumes thrown in there. By calculating these, it will allow you to draw a nice titration curve for the pH. And so I give you an opportunity there to draw it in your homework. You could also just, if you want to make it in Excel and paste it on there, that's fine too. Either way is fine there. When I give you the key, I have one already made in Excel. So now, last week we saw a complete run through of all the different situations you might run into for a strong base weak acid titration. This week for our first lecture, I have shown you every step or before, at, and after the equivalence point for a weak base strong acid titration. And so this should give you the tools you need to approach any problem like this, even if, for example, at the very beginning, before our titration started, we had a situation where we had to solve for the quadratic. During the titration, again, that probably won't happen to you because you'll end up in a buffer region where you can use the Henderson-Hasselbalch. Maybe at the equivalence point, you might run into that if the Ka for the conjugate or Kb for the conjugate is too large. You have to solve for the quadratic. But I just wanted to remind you that you could run into that. So I hope that was helpful. It does take a long time to run through all of these problems, and so I'm glad that I'm able to show you step by step. So you can always refer back to this for the strategy, or refer back to my slides. Just going back to my slides real quick before we end here. My slides for the acid-base equilibrium concepts, or the acid-base titration concepts. And the concepts are really, I'd say, the tough part here from last week's slides. Remember the steps that are laid out here. You figure out, you're going to have a change in volume, so you figure out the new molarities. Then you apply step 1, the stoichiometry step. And here you always assume complete reaction of the strong acid or strong base. But when you get to step 2, the equilibrium step, this depends on where you are in the titration. If you're before the equivalence point, you can use the Henderson-Hasselbalch equation. If you're at the equivalence point, all you'll have left is the conjugate acid of your weak base or the conjugate base of your weak acid. So you'll have to determine the Ka or the Kb for the conjugate and set up an ice table and do an equilibrium step or equilibrium calculation. If you're past the equivalence point, your pH will be decided by your excess strong acid or strong base concentration. The remaining weak acid or weak base will be negligible in its contribution to the pH. So you can always just refer back to this if you forget what it is that you're supposed to do. And so again, a lot of what you're going to do this week and last week is just a lot of practice. I highly recommend the problems in the book that have solutions within the chapter, and then for even more practice, I recommended to you additional problems that have the answers in the back. And you should continue to do these until you are regularly getting them right. Start with the ones in the textbook because they have full solutions within the 19.2 section in particular. with those full solutions they've got, and then move on to those suggested problems after you've done your homework. These take a lot of practice. And so for next week, I'll be giving you, for next week, we still have 1 week until the exam, but we don't have a whole lot of new material. So next week, I'll be doing some more problems with you guys on acid-base titration, and I'll be starting to introduce the next chapter that we're doing after the exam, which is chapter 20. That way, this will give us a little bit of time at the end to review before your big final exams and stuff. So in the next video for this week, I'm going to be doing solubility equilibria. So I'll see you in the next video.